2, we have equivalent circuit analysis of transformer, determination of the equivalent circuit parameters, and performance parameters of transformer. The last 2 points that are not included in this part. Maybe they will be added later, inshallah. Okay. So the first part, which is the most important part in the transformer, is the equivalent circuit analysis. So the equivalent circuit analysis of the transformer is a method of studying the behavior of this transformer. We said that this real transformer, we have a lot of physical phenomenon happens in this real transformer, and each one of these phenomena will be represented by a passive element. For example, here we have a resistance of the winding. So, and we have, for example, a leakage. The resultant representation of the real transformer taking into consideration the leakage flux. In this circuit you see here, this is not the last equivalent circuit of the transformer. This one is just the first step. Here we represent the ohmic losses of the winding, the internal resistances of the winding. We don't have an extra resistances. Those resistances are the internal resistance of the coils of the winding. We represent the ohmic losses by resistances in the primary and in the secondary. Also, we represent the leakage flux, the leakage fluxes by inductance or reactance. Of course, X is reactance. So here L indicates to the leakage. So we have a leakage in the primary and in the secondary. In this representation, the effect of winding resistance, which is ohmic losses, joule losses, heating losses, we can call them heating losses, of course, they are represented by a resistance R1 and R2. Also, the leakage flux is represented by leakage reactances. So, of course, X equals to omega L. So, XL1 equals to omega L1 and XL2 equals to omega L2. And the inductance, we have seen before that the inductance equals to the linkage flux or the flux over the current. So here, LL1, the leakage inductance, equals to N1 multiplied by the leakage flux over the current of the primary I1, and L2, which is the secondary inductance, equals to N2, the number of turns multiplied by the leakage flux in the secondary over the secondary current. So the first step in this analysis, we represent the resistance and the resistance and the inductance. Okay, so let's use the table. Is the voice is good here now?
Yes. Yes. Really.
Okay. So here we have a table, for example. So for firstly, we said that we represent the ohmic losses by resistance and the leakage by inductance. This is in the primary. Okay, of course, this is. Then we represent also the secondary by resistance and inductance. Okay, sorry for the bad drawing. Okay, this is the first step. This is the first step of equivalent circuit analysis. Let's move to the next slide. In practical transformer, the magnetic core has a finite permeability. So it has a specific value of permeability. So it has a specific value of reluctance. So in the first step, we have only represented the winding, the current, the resistance and the inductance of the winding. But here also we have other resistance and reactance of the core. In the ideal transformer, we neglect the effect of the core completely. the core has no reluctance, the core has infinite permeability, we don't have saturation, we don't have core losses. But in the real transformer, we consider all of these points. So in case of practical or real transformer, the magnetic core has a permeability, which means has a reluctance. So there is a current established in the core. We call it magnetizing current, or we can call it excitation current. So we are going to see the difference between them. Okay, so a magnetizing current will be created a core, which is this magnetizing current is the one who established the flux. So a magnetizing current created in the core, and this magnetizing current will create then the flux. Okay, so this current, this laser width, is the one who established the current. So firstly, we have represented here the resistance and the reactance of the primary winding. Here, the resistance and the reactance of the secondary winding. And now the parallel branch here represents the effect of the core. So the effects of the core can be represented by a magnetizing inductance called LM. It's a magnetizing inductance called LM. And also the core losses are represented by a resistance called RC. So we have done the same as we have done with the winding. In the winding, we have a resistance, ohmic losses represented by resistance. We have a leakage flux represented by a reactance. Also in the core, we have a magnetism. It has been represented as a parallel branch, and we have a magnetism inductance, LM or XM, and we have the core losses has been represented by resistance RC. Okay, so this parallel branch does not exist in the ideal transformer. This parallel branch does not exist in the ideal transformer, but it must be taken in the real transformer. And this part still representing the ideal transformer. This part can be omitted later. Okay, so here the second step, we represent the effect of the core. Let's go to the table.
Sir, why is the two in parallel, RC and XM in parallel, not in series?
XM, the effect of the core. The core, look, this effect of the core does not affect the current of the primary directly. Okay. We have a transfer between the primary and the secondary. If we represent it in series, so we should add it to the primary or to the secondary, but this effect is not in the primary and is not in the secondary. Those parts are separated. Since the transfer of the flux done through this core, it has been represented by a parallel branch, not in series. Okay.
Sir?
Yes,
Yeah.
but inside the
Sir?
branch, why is the resistance and the inductance in parallel, not in series, inside the branch?
Inside the why they are in series. Look, Anije, okay, why they are in parallel, not in series. Okay, the current flowing through resistance and inductance are not the same current. We're gonna see it. Okay, let's go to the table. Okay, so in this representation, we said that the resistance here of the winding, of the primary winding, then the inductance of the primary winding. Okay, this is the primary. Okay, the secondary, we have also a resistance of the secondary and the inductance of the secondary. The parallel branch, we have a core resistance, which represents the core losses, and we have a magnetizing inductance. Okay. So even if we take them in series, okay. So see the current here, I1, which is the primary current. Of course, the current here is the secondary current. The primary current get divided at this point. Here is the I2 prime, the secondary current represented in the primary. And we call the excitation current IE. It will divide it into a magnetizing current IM flowing in the inductance LM, and a core losses current IC flowing in the resistance. That's why we have separated them in parallel. Okay, so the primary current here, I1, is equal to what? Equals to the current I2 prime, which is the current of the secondary, or the transferred current. The transferred current, which is I2 prime, and I2 prime equals to I2 over A. I2 prime is I2 over A, which is the turn ratio, plus the excitation current. The excitation current is the current that flow in the core, or in the parallel excitation branch. So look, this current is too small compared to the current of the secondary. That's why, for example, in the ideal transformer, we neglect the effect of this parallel branch, and this excitation current equals to IC, which is the current of the core losses, plus the current IM, which is the magnetizing current. Here we should separate between the effect of the core losses and the effect of the magnetizing. That's why we represent those resistance and reactance in parallel. Okay. Is it clear, this second point, before passing to the next point? You should take notes, because this is very important. Yes? The meaning of XM. The meaning of XM. XM represents the magnetizing effect of the core. Okay. You didn't get the connections. Okay. How we can explain it? Okay. So the first connection of the core. The first connection of the core of the primary and the secondary winding is clear, I guess.
Sir. Sir, actually, my question wasn't. It was about the real meaning of the connections. Why do we place the excitation? I mean, both the resistance of the core and XM in parallel. I didn't really get this.
Between them in parallel, you mean, or with the primary, or with the secondary?
With the primary and the secondary.
Okay. Why they are in parallel? Okay. Look, so we said that in this practical transformer, there is a part of from the current has been taken, which is the excitation current. If we represent them in series, the same current which flow in the primary will flow in this parallel branch. But and this is wrong. For example, if we represent them here, for example, the same current of the primary which will be transferred to the secondary, which is the load current, will flowing through this parallel branch. So there is no direct connection between the core and the winding. So the connection between them is through the flux. That's why a part from the current has been taken, because it's some kind of losses. It has been neglected in the ideal transformer, has been taken to establish the flux in the core, and we call this excitation current. This one cannot be represented in series because it does not have a direct connection with the primary or with the secondary.
Yes, sir, it's clear now.
Yes, I hope it's clear for the others too. Okay, I'm going to repeat. I told you this is the main part in the transformer, which is the equivalent circuit analysis, and most of the problems are based on the equivalent circuit. We will repeat. At the beginning, in the first step, we have represented the effect of the ohmic losses in the primary winding and in the secondary winding by resistance and the leakage reactance. You have seen here a resistance of the primary winding, the leakage reactance of the primary, here also the leakage reactance of the secondary and the resistance of the secondary. In the first step, we have been represented only the effect of the winding. In the next step, we said in the practical transformer, the effect of the core exists, not like the ideal transformer. The effect here of the core, because the core losses are considered, the saturation is considered, the reluctance exists. We don't have an infinite permeability. That's why a current is required. There is a current is required to achieve the flux. This current required to achieve the flux called a magnetizing current. Here we represented by excitation current. If we neglect, for example, the core losses, the magnetizing current, it will be equal to the excitation current. But in general, it's the excitation current. We said that the core does not have a direct connection with the primary or the secondary. They are connected by the flux that created in the core. The current of the primary will be transferred to the secondary through this flux. Apart from this current will be taken, apart from this flux will be taken to create this flux, and we call this a magnetizing current. So for the one ask me what the meaning of XM, XM or LM is the magnetism, or is the magnetism inductance or reactance. So if this reactance depend or related with the leakage flux, this one is related to the linkage flux. Okay, so XM is the linkage flux, reactance or the magnetism reactance or inductance. I hope that this point is clear before continue. Okay, so we said that this parallel branch, since an amount of current is required to create the flux, which is the linkage flux, not the leakage. The leakage flux is represented here by inductance, but there is a current required to create this linkage flux. We need this inductance, which is XM or LM. Also, since the core losses exist, let's represent them by a resistance called RC, which is the core losses. So here, the primary current will be divided, and in this point, to I'2, which is the current transferred to the secondary, plus the excitation current. Remember that the amount of the excitation current is too small compared with the current transferred to the secondary. The transferred current is I2 prime, which means I2 prime equals to what? As we have seen in the impedance transfer, I2 prime equals to I2 over A. And A is N1 over N2. So I2 prime is the secondary current referred. So focus a lot on this word, which is referred. We are going to see it a lot later. Referred. Okay. Referred or reminded, for example. Okay. So this is the secondary current referred to the primary. Okay. So this is the transferred current or the secondary current referred to the primary. IE called the excitation current. The excitation current divided into the core losses current and the magnetism current IM. IC is the core losses component of the excitation, which RC, and IM is the magnetism, the current of the magnetism component, which is XM or LM. Let's see now the next slide. Okay. So here, this is the step number 3. Step number 1, we have represented the effect of the winding and the ohmic losses and the leakage fluxes. Step 2, we have represented the effect of the core by the parallel branch, which called the excitation branch, represented by a core losses resistance and a magnetism inductance that establish the linkage flux. Step number 3 is so important. We should try to focus on this. Okay, so here, firstly, the ideal part, the ideal transformer part have been moved. So this part will be omitted, it's not important. Okay, the ideal part of the drum has been moved to the left, referring all the quantities to the primary. So the secondary is the part after this. Okay, This part only indicates the transfer of, we kept just to indicate that we have a transfer between the primary and the secondary. This part has been moved. Here, the primary is in the middle. In the next step, we have moved this part here. By moving this part to the terminal of the transformer, all these quantities become in the primary. Okay. All these quantities, which are the leakage reactance of the secondary, the resistance of the secondary, the EMF, E is the EMF. Look here in the ideal transformer, we said that E is the voltage here, the voltage here in the parallel branch. In the ideal transformer, this EMF equals to V, because those part does not exist. Resistance and inductance does not exist because they are their effect is neglected. So V equals to E, which is the EMF. But here, of course, if we done Kirchhoff's law, V equals to E plus those voltages, which is Ri and Xi. Okay. I think we can explain it better in the table. Okay. Firstly, what does it mean referred? Okay. Referred معناها رجعناه. We take all the secondary quantities or secondary parameters or secondary values, have been put them in the primary. Of course, they will not transfer it directly. We have seen in the impedance transfer, if the impedance and the same with resistance and inductance, for example, R2, which is the secondary resistance, appears in the primary as A square R2, and X2, which is the secondary inductance or reactance, appears in the primary as A square in the primary, and we can call it also R2 prime and X2 prime. The current of the secondary appears as A square over A2 over A in the primary. Also, the voltage of the secondary appears as A V2. Is it clear how we referred those quantities before passing this point? I think it's شوية. Okay, معلش. We're gonna repeat it. Okay. So why we do this referred equivalent circuit? In order to simplify, to study all the quantities in one part, in a single part. We study them, all of them in the primary, all of them in the secondary. So we can take the primary, the referred equivalent circuit to the primary. Also, we can do the same with the secondary. Okay. So here we have seen, that's why I have done the impedance transfer in the beginning as an introduction to this point. Okay. So by moving the ideal transformer part to the terminal, all the quantities of the secondary become or appear in the primary. So when the resistance or the impedance of the secondary appears in the primary, it will be appears as A square times R. X2, the reactance, the leakage reactance of the secondary appears in the primary as A2, A square X2. Also, the current of the secondary appears, I2 appears in the primary as I2 over A, which is I2 prime. Also, the voltage of the secondary V2 appears in the primary as A V2, which is V2 prime. Also, we can write here R2 prime and X2 prime. this is the meaning of referred parameters. Generally, the ideal transformer part is not showing the equivalent circuit referred to the primary. So that part we can omit it. We don't need to represent it. Therefore, the final transformer equivalent circuit referred to the primary is shown in the figure number 12. So this is the step number 3. The final referred circuit to the primary here is the figure number 12. So we started from the beginning. At the beginning, we have represented the effect of the primary winding. So the primary parameters stay the same because they are in the primary. They has not been moved to the other part. So R1 stay R1 and X1 X1. Then the parallel branch which indicates or represent the effects of the core is represented by a core resistance or core losses RC and XM, which is the magnetizing reactance. Then the secondary quantities, the ones has been moved to the primary or appears in the primary, does not move it physically. They are not moved physically to the primary, but we can see them from the primary. Okay, the resistance R2 of the secondary equals to A2 square times R, and the leakage reactance of the secondary equals to A square X2. The current, transferred current of the secondary, we can see it in the primary as I2 prime, which is A2 over A. Even if we have a load, for example, if we have a load Z of the secondary, ZL, it appears in the primary as A square Z, ZL prime. Also, the voltage appeared as A V2. So the voltage multiplied by A, the current divided by A, and the passive, the resistance and the inductance multiplied by A square. Here I put quiz for you. Derive the equivalent circuit referred to the secondary. So if we don't do it with the secondary, it will be vice versa. Okay, it will be vice versa. So if we do it with the secondary quantities, of course, stay the same, and the primary resistance and primary leakage inductance must be divided by I square, not multiplied by A square. Here divided, it's vice versa. Also, the current of the primary represented in the secondary will be multiplied by A, the turn ratio, and the voltage which will divide it. Everything is vice versa. If we need, I can give you some exercises. I ask you to give me the circuit referred to the secondary. Okay, here in the course I give you one case. We can deduce directly the other case. Okay, let's try to. It's L, not 1. Yeah, L. It's L, not 1. Okay. Yes, it's L, which means load. Okay. The parallel branch has not been reminded to the primary or to the secondary. We're going to see it in the next step. Okay. Which this is, okay. Before passing to the next step, okay. To this meaning or to this definition, we call this circuit the exact equivalent circuit referred to the primary. The exact equivalent circuit referred to the primary. Also, we can do the exact referred equivalent circuit referred to the secondary. I will try to conclude this part before passing to the next part. It will get more complicated. Okay. So, okay. Step number 1, we said at the beginning, we represent the resistance and the inductance of the winding in the primary and in the secondary. So this is the primary, this is the secondary. We have resistance, we have an inductance. Okay, this is primary, this is the secondary. We can call this R1, leakage inductance X1 or reactance X2, and R2. Those are the parameters of the winding, primary and the secondary. Then we represent the effect of the core, which exists in only the practical transformer, does not exist in the real in the ideal transformer. So the parallel branch, the effect of the core represented by the inductance depends on the linkage flux, not the leakage. This one depends on the leakage. X1, XL1, XL1, XL2 depend to the leakage flux. Here in the core, the inductance depends on the linkage flux. We call it LM, which means magnetizing. This is the inductance here, LM. And the losses in the core represent them by a resistance called RC, which is the core losses resistance. So the current here of the primary I1, before it transferred I1, before it get transferred to the secondary, the transferred current is I2 prime. There is a part is taken from the current, which is the excitation current, IE. So I1 equals to what? Equals to the current will be transferred to the secondary, I2 prime plus IE. And also IE is IM, which is the magnetizing current flowing through the magnetizing reactance or inductance plus the current flowing through the core resistance, the current of the core losses. And be careful here, there are vectors, okay? They are vectors. Later we represent them as RMS or as cosine and sine. Okay, so this is the equivalent circuit, not referred, not to the primary or not to the secondary. This is the equivalent circuit. Then we pass to the referred equivalent circuit. In the referred equivalent circuit, we have omitted the part of the ideal transformer. Then now we are seeing all the quantities of the secondary in the primary, and we said in the impedance transfer that to see when the resistance and inductance of the primary appears in the secondary, it will be multiplied by a square. Also, the inductance will be multiplied by a square. The current, which is I2 prime, هو I2 over A. It will be multiplied by the 10 ratio. Also, the voltage of the secondary V2, when it appears in the primary, it is represented by V2 prime. V2 prime appeared in the primary equals to what? Equals to A V2. Okay. So RC and XM, it's not important to transfer them. You can find them here or here because they are connected in parallel. Okay. Now this is, we call this with me, this is the exact equivalent circuit. إشفاو على كلمة exact, because we are going to pass to the approximate equivalent circuit. There is an exact or there is an approximate. So before passing to the, of course, this is exact equivalent circuit referred to the primary. Exact equivalent circuit referred to the primary. Now let's try to represent the exact equivalent circuit referred to the secondary. Okay, let's try to do it. Of course, it's the same. Okay. It's the same. It's not the same, in similar way. Okay, of course, we assume that we are in the secondary. Here, okay, let's draw, let's clean those. Okay, assume that we are in the secondary. Okay. This is the resistance. Of course, if we are in the secondary parameters stay the same. For example, this is R2 and this is X2. If we are in the secondary, but R1 gonna divided by I square. So it's vice versa. Before it's, sorry, A square. And X1, it will be divided by A square also. The voltage of the primary V1, it will be represented by V1 over A. And the current of the primary, the current of the primary appear in the secondary as I1 prime, which is A I1. Okay. I1 prime. Okay, this is now the equivalent circuit referred to the secondary. Exact equivalent circuit referred to the secondary. Is it clear? Yes? Okay.
Yes.
Try to repeat it 1, 2, 3 times. You will, because inshallah, if we have time, maybe. Yes, of course, there is a recitation, yeah. Inshallah, if we have time, or in the future, for those who will study power engineering, who will study the induction motor, you will find a similar. But only in the motor we said stator and rotor, referred to the stator, referred to the rotor. Referred to the stator, referred to the rotor. In the transformer, referred to the primary, referred to the secondary. I repeat a lot concerning this part because I see it the most important part in this chapter. And also I see this, consider this chapter, transformer is the most important chapter in the module. Okay. So this is the exact equivalent circuit referred to the primary and referred to the secondary. Now let's see another circuit, which is the approximate equivalent circuit. What does it mean, approximate equivalent circuit? You know what does it mean, approximate? So the voltage drops. Okay, so R1 and I1 and I1 X1, they are voltage drops. They are voltages, are normally small compared to the voltage V1 here. Of course, they are small. In addition, the excitation branch has very small current. So the current flow here, the excitation current here, IE, is too small compared to the primary current. So I1, IE is too small compared to I1. Okay. The excitation branch has very small current in comparison to the load current of the transformer. Therefore, this branch can be moved to the input terminals. Okay. So you see here the parallel branch was in the middle. Okay. So this is the parallel branch. Since the current flow through this parallel branch is too small, it's not important. This branch can be moved to the input terminals like this. Okay. And the voltage across the voltage which is across this parallel branch, which is the excitation branch E1, is almost equals to V1, almost. And the current through this parallel branch is too small. We can move it to the input. And we call this approximate equivalent circuit referred to the primary. This is the difference between exact equivalent circuit referred to the primary or referred to the secondary, and approximate equivalent circuit referred to the primary or referred to the secondary. In the approximate equivalent circuit, we move the parallel branch, which is the excitation branch, to the input. Okay. Why we move it? In order to simplify more the circuit. Okay. Why we move it? In order to simplify the circuit. If we move the parallel branch, we can add this resistance. Okay, look here. When we move this excitation branch to the input, we can add this resistance to this resistance, and we can this inductance to this inductance, because they become in series. Okay, so if they become in series, we can add them. So the primary and secondary impedance can be added to each other, and we will have an equivalent resistance, include the primary and the secondary referred resistance. So R1 equivalent equals to R1 plus A square R2, and the inductance will be added to each other. So X1 equivalent equals to X1 plus X plus A square X2, and this is approximate equivalent circuit referred to the primary. If this one is referred to the secondary, R equivalent become, of course, R2 plus R1 over A square. If this circuit is referred to the secondary, since it's referred to the primary, so the equivalent resistance of all the total, يعني جمعنا لي resistance مع بعضها, the equivalent resistance equals to R1 plus A2 A square R2. X equivalent equals to X1 plus A square X2, and we call this approximate equivalent circuit. This is for the purpose of simplifying the equivalent circuit. So you can see where we started and where we and what we get now. We start simplifying step by step this equivalent circuit. At the beginning, we referred all the circuit to the primary and or to the secondary. Then we do this approximation by moving the parallel branch into the input in order to add those resistance, and we can get this approximate simplified equivalent circuit referred to the primary. Okay. Okay, X does not, G does not go on. Sometimes they write it, sometimes they didn't write it, but G of course exists because it's a reactance. Okay. So here, if we want to, for example, if we want to pass from this to the approximate equivalent circuit, of course, what will we do? We will move this part, the parallel branch. Why we move the parallel branch? In order because now here, if the parallel branch in the middle, we cannot add the resistance to each other and the inductance to each other. But if we move this parallel branch here, if we move this parallel branch here, now we are able to add R1 to A square R2, and we can add X1 to A square X2. And we call this approximate equivalent circuit referred to the primary. And the circuits become like this, become more simpler. We have only one resistance, which is R1 equivalent, and we will have one inductance, which is X1, which is X1 equivalent. And we have also the parallel branch here. R1 equivalent equals to what? Equivalent, of course, equals to R1 plus A square R2. The secondary resistance referred to the primary. X1 equivalent equals to X1 plus A square X2. So this is a simplified approximate equivalent circuit referred to the primary. Okay, hope everything is I hope until this point everything is clear. Before passing to the next point, this part is very important in the studying of all electric machines, not only the transformer. If we get the induction machine, we will see similar things, inshallah. Okay. Now, for a further approximation, so we more simplifications, we omit the parallel branch completely, because if we consider that we can, you are not obliged to omit it, or it's not necessary to omit it. Sometimes we need it, of course. For example, when they ask us to calculate the core resistance or the core magnetizing inductance, but here, if we can need more simplification, we can omit the parallel branch, because the voltage was here across the parallel branch is equals to the input voltage. Okay, almost the same. So the equivalent circuits become like this. So here, approximate equivalent circuit referred to the primary without the excitation branch. So I will repeat, we don't always omit it. Sometimes we don't need it. We were going to see it for some purposes we omit the parallel branch, not always. Okay. And of course we will have only one resistance and one inductance. You know, R1 equivalent equals to R1 plus A square R2, X1 equivalent to X1 plus A square X2. In similar way, the approximate equivalent circuit referred to the secondary, the R1 equivalent and R2 become different. So R1 equivalent become R2 equivalent, which is R1 over A2 square plus R2, and X2 equivalent became x1 over a square x2. This is in case of secondary, because in our recitation or in our problems, we will have different cases, not always referred to the primary, or sometimes I ask you to give me the circuit referred to the primary, or sometimes I give you the circuit referred to the primary or referred to the secondary and ask you to calculate such quantities. That's why you need to know the both cases. Okay, so this is concerning the equivalent circuit. The next step is the Phasor diagram. Before passing to the next to the Phasor diagram, let's repeat quickly from the beginning. So the equivalent circuit, the first things we have represented the effect of the winding by the ohmic losses represented by resistance, the leakage flux represented by reactance in the primary and in the secondary. Then the second step, we have represented the effect of the core by the excitation branch. Why? Because the linkage flux that will be created in the core requires which is called a magnetizing current. This magnetizing current will be taken from the primary current, of course. This magnetizing current will be taken from the primary current. We represent the linkage flux, not the leakage. The linkage flux will be represented by the magnetizing inductance or reactance XM. Also, the core losses are represented by resistance RC. This was the next step. The third step, we have seen the referred equivalent circuit. What does it mean, referred? We take all the quantities of a part of side and we move it all to the other side in order to simplify the study. And we have seen the circuit referred to the primary, when the secondary quantities have been moved to the primary. And when those quantities moved to the primary, for example, the resistance must be multiplied by A square, inductance must be multiplied by A square, the current must be divided over A, and the voltage must be multiplied by A. Also, if we have a load, also the load is like the impedance must be multiplied by A square. This is for the prime case of referred to the primary. If we have the other case referred to the secondary, it will be vice versa. The secondary quantities will stay as they are, and the primary quantities will be resistance and inductance divided by A square, the voltage divided by A, and the current multiplied by A. Then we have seen the more simplification, which called the approximate equivalent circuit. In the approximate equivalent circuit, we move the parallel branch to the input. Why we move it to the input? Because the voltage across this parallel branch is almost equals to the voltage of the input. Also, the current flowing through this parallel branch is too small compared by the primary current. And we move this part to be able to add the primary quantities to the secondary quantities. And we will get a simplified approximate equivalent circuit referred to the primary. We will have only one resistance and one inductance. And those are the equivalent resistance and equivalent reactance. And if we want to omit the parallel branch, this is the most simplified equivalent circuit of the transformer. Okay. Why we do this as most simplified? For the next step, which is the Phasor diagram. We have seen before in our courses, even in the first semester, the importance of Phasor diagram. Always when we work with circuits, the circuit gives us information about the magnitudes, but it does not give us information or a clear idea about the phase. Since here we are working with AC, not DC, we will have a phase. Okay, so this is the phasor diagram of the transformer. So the figure number 16 illustrates the phasor diagram depends. So the phasor diagram, it depends on the power factor. Why? Because when it's lagging or unity or leading power factor, the phase is different. The phase sometimes positive, sometimes is negative. Sometimes the current lag behind the voltage, and sometimes the current lead the voltage. So to represent this phasor diagram, we base on the last equivalent circuit we have. Of course, here we don't have a parallel branch. If we add, for example, a parallel branch, this parallel branch must be represented also here in the phasor diagram. But this phasor diagram is based on this equivalent circuit. So let's go to the table to see how we can get this phasor diagram. So since it's a circuit referred to the primary, the primary without a parallel branch, we're going to represent the phasor diagram like this. Okay, let's clean everything. Always, I told you before, in the phasor diagram, we have to choose a reference. And always a reference is represented by a horizontal vector without any phase. For example, here, you can see here the voltage, the output voltage, IV2, referred to the secondary, represented by this is the output vector, VI2, represented by AV V2. Let's start with the first case. The first case is with a lagging power factor. Okay, lagging power factor. So here, the current here, A1, it can be A1 equals to A2 over A. It's the same current. The voltage V and AV2. So firstly, we represent the voltage. Then we have the current that has an angle between the current and the voltage, of course. This is the phase. So this is the current, I1, or it equals to also to I2 over A. So this is the current, the voltage, and the current. So let's to clarify things, draw a mesh here. Okay, let's draw. Okay, let's draw a mesh here. Okay, so V1 equals to what? Equals to all these voltages. Okay, according to Kirchhoff's law. So equals to IA V2 plus the voltage across this resistance and reactance. Okay. So the voltage across the resistance, since the resistance, the voltage across the voltage across the resistance is Ri, and will be represented like this. This is the voltage across the resistance, Ri. Ri1 or Ri2 over A. And the voltage across here, we cannot add voltage to the current, but here we add voltage to a voltage. Okay, so we add here voltage to a voltage. the voltage across the resistance is RI1. The voltage across the inductance, of course, the inductance between the resistance and the inductance, we have 90 degrees. So this is the voltage across the reactance or the inductance. Okay, between them 90 degrees. And the last one is the input voltage. The input voltage is the summation of all of them. This is V1. Okay. So this is the Phasor diagram. This is, to be honest, is a simplified Phasor diagram because it's based on most simplified circuit. If we consider the parallel branch, this Phasor diagram will be more complicated. Okay. So is it clear how we draw the Phasor diagram?
Sir, will we consider the parallel branch in our work?
If we consider the parallel branch here, the current A1, the current A1, it will be divided to IE. So we need to also to represent IE here, the excitation current. We will add it. Okay.
Okay, thank you.
So this is the Phasor diagram. Let's repeat it quickly. See, this one is with lagging power factor. Okay. So we said at the beginning, always we choose reference according to this mesh. So the first voltage is V2. The voltage has an angle with the current like this. The voltage will be added to the other voltages, the voltage across the resistance, and the same phase with the current, and the voltage across the inductance shifted by 90 degrees to the voltage across the resistance. So this is, and the summation, of course, this one. This is the voltage across the input voltage. So let's write them. This is AV2. This is A1 R. This is A1X. And this is V1. This is in case of lagging power factor. Let's see the other case when we have unity power factor. When we have a unity power factor, of course, there is no phase between the voltage and the current. Okay, so we represent this is as the voltage. Okay, we represent this as the voltage. The current has the same phase with the voltage. Okay, so there is no phase between the current and the voltage. Also, the current across the resistance will have the same phase. Let's choose another color. Okay. The current across the resistance will have the same phase, so it will be added like this. This is the current across the resistance. While the current across the inductance or reactance always shifted by 90 degrees, like this. Okay. And the summation, the input current, become like this. Okay, let's choose another color. Okay. Okay, so this is the input voltage. So let's write them. Okay. This is the voltage AV2. The current has the same phase with the voltage A1. The voltage across resistance RA1 has the same phase. The voltage across the inductance is shifted by 90 degrees, which is I1X. So here R and X are the equivalent, not R of the primary and R of the secondary. It's the equivalent resistance and the equivalent inductance, because we have based on the most simplified equivalent circuit. For example, if we take another equivalent circuit, it will be more complicated, especially if we consider the parallel branch. So the excitation current must be involved to the Phasor diagram also. And this one, this is the input voltage. The last case, the case of leading power factor. If we, for example, have a capacitive load, this is the voltage always chosen as a reference. Now, the current is like this. The current. So this is the shift between the voltage and the current. Theta. Then the voltage across the resistance has the same shift angle with the same shift angle with the current, of course, like this. And the voltage across the inductance is shifted by 90 degrees. Shifted by 90 degrees to the voltage across the resistance, so it becomes like this. Okay, so this is the Phasor diagram and the summation. The summation, of course, the summation, the start point with the last point. This is the summation. Okay, sorry. Okay, of course, the length of the vectors is depend on their magnitudes. Here we are just drawing, but of course the length of those vectors depends on their magnitude, of course. So if this the voltage across the inductance, the input voltage become like this. We connect the first beginning with the last end. This one is V2. This one is the current I1 or I2 over A. This one is the voltage across the resistance Ri. This one is the voltage across the inductance Xi, and this is the input voltage V1. And those are the Phasor diagrams of the transformer in the three cases. You can see them here. And if it's the circuit referred to the secondary, of course, they are similar. The difference only with the values of R equivalent and X equivalent. We still have another point, which is the determination of the equivalent circuit parameters. How we can calculate R1, X1, R2, X2, RC, XM. We can calculate them through different tests. We have different experiments, and unfortunately, especially this part should be done in the lab, to understand more the transformer, because those methods are experimental methods to calculate the parameters, determination of the equivalent circuit parameters. It's a very good lab. Okay, so we will have some tests. The first test is the open circuit test. The second test called the short circuit test. So through these tests, we can calculate the values of all these parameters, and we will have an example, inshallah. We're going to see them next time. We have an example how we can calculate the equivalent circuit parameters. So this element will be led to the next time, inshallah. I think we can stop here. Next session, inshallah, maybe on Tuesday.